Hi everybody. Can you hear me at the back? Yeah, awesome. So welcome to my talk. I'm going to be talking how to hack the Java compiler. So before I start, I always like to ask a question to kind of gauge the audience. Who likes beer in the room? Very good. But the most important question, who likes Belgian beer? Wicked. So I was born in Belgium, in Brussels. At the moment, I'm doing a PhD at the University of Cambridge. And I'm interested in how to evolve programming languages. So Java is a programming language that's been there for a while. So it's quite difficult to add new things to it and keep it backward compatible. So based on that, my research has been about scalable source code analysis and automated refactoring. Before that, I did my undergrad at Imperial in London. And I worked for a few companies on some projects. Right now, what I'm trying to do is start an IT consultancy because I realized, well, I love working on projects and I kind of like teaching my students, so I'd like to take that a bit more seriously. So let's get started. So in this talk, I'd like to give a brief introduction to what a compiler is first. Then I'll show you how you can implement new features to Java by simply modifying the compiler. It's not that difficult. And then I'll show you how you can leverage the different APIs that exist around the compiler. So what is a compiler? So a compiler is a piece of software that just takes a source form and converts it to a target form. The way I like to think about it, it's like a language interpreter, as in like a person. So in Belgium, we've got a little problem. So people speak Dutch, people speak French, people speak English. So it'd be really nice if we had like compilers, you know, to translate French to Dutch and Dutch to English. So that's what a compiler does. In general, we refer to the term compiler because it compiles down to a lower level language. But recently, it's very kind of trendy to compile any high-level language to JavaScript. And Dart, Kotlin, Ceylon are a bunch of them. So there are some talks about it. So you'd think that, well, it sounds quite easy. But compilers are a really, really big technical piece of software. So GCC has been developed for 20 years and has more than 4 million lines of code. So here's a very, very simple example. You take a Java class, and then the Java compiler will output Java bytecode. And this is how it looks for a simple Hello World example. So how does it work? Well, there are 5 phases in the compiler. There's the lexical analysis, the parser analysis, semantic analysis, then it may or may not do some kind of optimization, and finally, it will translate it to the target form. So what exactly is the lexical analysis? So the lexical analysis takes your source code and will translate that into tokens. So this is quite useful because this kind of representation is decoupled from the concrete syntax. And we can use that in the next phase, the parser analysis. So the parser analysis will check if your code is structurally correct. And based on that, it will then generate an abstract syntax tree. So if you take that example, that is an if condition, it will just build a little tree out of it. And this is quite nice because we get a structural form of the source code. So what's the next step? Next step is, well, we perform various semantics checks. For example, is a method defined? When you have a method call, was it defined? Are you allowed to assign this type to another type? Is this code reachable at all? So that's what a semantic analysis phase does. Afterwards, some compiler do optimizations. And an optimization, the whole point of it is just to give you a more efficient version of your code. So some example of optimization could be dead code elimination. So what that means is maybe you're defining a variable that holds some value, but this is never used in the future. So, well, we don't really need it. Common sub-expression elimination. So if you've got an expression, let's say A times B, that is reused in some other place of your code, well, maybe we don't need to recompute it every time. Maybe we can put in temporary variable. So that's an example of optimization. Inlining, method inlining. So this is kind of like the summary of all those steps. And the final step is, well, we just convert the optimized tree into the target code. So where is this going? Let's see how this works with the Java compiler. So if you want to download the source code for the compiler, just use this command line, ag-clone with the URL. So this will download the latest source. The compiler source itself is in the langtool CRC directory. There's a nice build file. First, you have to set up the build properties to say where your JVM environment is, and then just type ant, and that's it. You wait 40 seconds, and you've got a nice binary in the dist bootstrap bin. So, I've talked about all those different phases. How does that relate to the Java compiler? So the lexical analysis is available in this class called scanner. The parser analysis is in the JavaC parser. Semantics analysis is on the ATR, and then for translation we've got one that's called gen, that just generates bytes code, and lower, which is a phase that desugares code. For example, you know, generics are erased, so this phase would be responsible for that. And turns out the Java compiler actually doesn't do any optimization. It's just a bytecode translator. Optimizations are handled by the hotspot. So let's do something fun. Say I'd like to implement the Elvis operator. So the Elvis operator is available in many languages like Groovy, for example. And it's really just a coding pattern that checks if the left-hand side is null or not, and based on that, we provide a default value. So, for example, this statement, string s equals maybe null, then you have the Elvis operator. So, the reason it's called Elvis operator, if you kind of try and flip your head to the side, you'll see that he's got like curly hair. So, that's why they call it Elvis operator. So, the variable s here could have two values. It could be maybe null, which is another variable, or backup default string. If maybe null is actually null, we give it the default value. Otherwise, we retain it. And this can be desugared in the following manner. So if I've got E1, Elvis, E2, then first we create a temporary variable that stores E1, so we evaluate that expression. We check if this is null. If it's not, then we reprovide that temporary variable. If it is null, then we evaluate the expression E2. And this feature was actually proposed in Java 7, but was not retained. So what do we have to do to implement the Elvis operator? Well, there are two steps. One is we have to modify the lexical analysis, so it recognizes the Elvis operator and makes a token out of it. And the second part is, well, let's modify the parser, so it recognizes a new expression type with the Elvis and does a translation. So, if you want to see how this is done, there's an article, How to Hack JavaC, in the Java magazine. But I'm going to show you how to do it live. And let's hope this works, because it's always tricky to show code in a presentation. So this is Eclipse. So I like to add a new token that recognizes the Elvis operator. A good place to look might be, let's find files that have token in the name. So I've got one here. And I've made a modification here, and we can see here, we've got an enum class called token kind that has a bunch of different tokens. For you probably recognize abstract, which is spelled abstract. This is quite easy. And here we go. I've just added the Elvis operator. Cool, so step one finished. Just add this line. And anytime question mark colon is there, it'll be replaced by the token Elvis. Cool. So next step is we need to modify the parser. So as I mentioned, is the class JavaC parser. And we're interested in parsing an expression. So the Elvis is a new type of expression. So let's see how the Java parser does it. Well, first of all, it just forwards this to a method called term. Cool. Let's see what's going on. Some kind of a previous mode and things, some kind of a birthday here. But most importantly, the expression is handled by this method called term, which is overloaded. So let's see how this works. Great. Another method that does parsing, term1. So let's see how this guy works. Cool. So I'm arriving to term1. So this code wasn't there before I added it. So the only code you had was this. So what it does, it checks if the current token is a question mark. If it is, it forwards this to term1 rest. So let's see what term1 rest is. Maybe we can kind of copy what it does. So these recognize expressions of this form, and this is the conditional expression, right? So if the token is a question mark, great. We'll parse it, left-hand side, and then we parse the right-hand side, and we create an abstract syntax tree node conditional. Cool. So maybe we should do something similar for the Elvis operator. So here it is. I'm checking if the current token is Elvis. And I'm deferring that to time one Elvis. And this is the code for it. So we pause the right-hand side of the Elvis expression. And what we're interested to do is translate Elvis to a conditional expression. So what I have to do is, if E1 not equals to null, then provide E1 back, assuming that there are no side effects. Otherwise, we give the expression E2. So this is what I'm doing. I'm parsing the E2 expression. Here I'm creating the literal null. Based on that, I'm creating the predicate that checks if E1 is not equal to null. So this means not equal. This is the operator, this is expression 1, and this is the literal that I just created. And finally, we just create an abstract syntax tree node conditional that takes that condition, the expression 1 and expression 2. And this is it. Afterwards, this gets propagated and will be translated to Java bytecode. So I think I have time for a quick demo. So perfect. So here's a test file. Right? So hello, devox null. Then we've got the Elvis operator here, devox, and then some question marks. So obviously this should print hello, devox, exclamation mark, exclamation mark. So if I use the standard Java compiler, so first let's check which version I've got here. Perfect. So if I just use the standard Java compiler, it will complain and say, I don't recognize this. This doesn't exist in the language. If we use, so this code, I built it, so I've got a new compiler, and as I said, this is available in this directory, this bootstrap, bin, and then I've got a nice version of Java-C, E1, and I compile this file again. It doesn't complain, great, so let's see what's going on. There's a .class generated. We run it, and cool, I just got a new feature in Java, amazing, in 10 minutes. So, if you want to, this is available, as I said, in this article. So all the code and all the details are available there if you want to have a little play. But I find when you hack, the hardest thing is always which place do you need to hack? And once you figure that out, then it becomes easy. So let's go in the second part of my talk, the third part actually, which is let's befriend the Java compiler. So the Java compiler has a bunch of API that are useful. So you've heard probably a lot about lambdas coming in Java 8, default methods, but the compiler also has a new feature called compiler plugins. So I'll quickly explain you how you can use them. So a compiler plugins allows you to add new functionality, new faces to the compiler, but without modifying the code base. So you can encapsulate the behavior in a jar, in a plugin, and then distribute it to people. And they can use that. The API is still experimental, so what I'm going to show may or may not work in the next months. But Jonathan Gibbons, who's the technical lead, has assured that it will work, so finger crossed. There's an article about this functionality coming up in 2 months in the Java magazine, in case you'd like to read about this again. So what can you do with a compiler plugin? Well, you can add extra compile time checks, for example. If you want to enforce, let's say, a coding standard in your code base, you could do that as a plugin. Maybe you'd like to do some automated refactoring of code. Well, you could do that using a Java plugin, compiler plugin as well. And if you want to do some kind of customized source code analysis, then you can also use a plugin. So what I mean by customized source code analysis is, say you'd like to infer some kind of software metrics in your code base. Then you could write a plugin to do it. And here are the steps needed if you'd like to write a plugin. So there's an interface. Can you guys read? Let's see. Yeah, perfect. So it has just two methods. One is getName, and the other one is call. So the call method gets a Java-C task back. So a Java-C task object encapsulates functionalities from the Java compiler. And this is how it looks. So you can analyze files, so that would do the semantic analysis. You can generate files, so that do the translation, so generate .class files. But interestingly, it has an add task listener method. So what is that about? So a task listener allows you to kind of hijack different events generated by the compiler. And it has two methods. One is started, so that's when the event is just starting, and the other one is finished, when the event is finished. So next question might be, well, what kind of events can I hijack? So some of those events could be pause. As soon as the compiler is pausing a file, you could listen to that and do something about it. One could be analyze. So when the compiler is doing semantics checks, then you could hijack that. There would be kind of generates. So if you want to do some code translation, do some refactoring, then it might be a good idea to hijack generate. And I'll show you a quick demo how you can use that. And here's the example. We like to find code that is checking for a null result from calling get on a map. So you might say, this is easy, but let's take this code example. I've got expression.get that takes a key equals null. So I need to find out what's the type of expression. It could be, it has to be a map, it could be a hash map or any other subtype of map. I have to check that the method get is actually called on that and see if the whole expression is checked for null. So the code is available on GitHub, so if you'd like to follow that. And again, I've got some time, so I'll show you some code. So I've called my plugin code pattern plugin because it finds this specific code pattern. So as I said, we have to implement two methods. One is getName, so code pattern plugin, and this will be recognized by the compiler when I inject the plugin. And the other one is call. So I like to hijack some events, so let's create a new task listener. Let's see how this is defined. There you go, so I'm implementing task listener. I don't care about started, but I'd like to hijack any events that has to do with semantic analysis. So here it goes, task event, get kind. If it's a semantic analysis, great. We're able to get the current source file that is being targeted, like this. So a compilation unit is actually the abstract syntax tree representation of the source code file. And then I'll pass that on to my visitor. So the visitor is what's actually going to go through that source file and see if the pattern exists. So I don't want to go so much into details about this visitor. So the code is available, you can have a look at it, but basically I'm going to create, for example, a type here, which is the java.util.map. I'm going to create a name that represents the method that I'm trying to look at. Here, visit binary is a method that will check every time there's a binary expression, then this will get called. So I'm able to kind of extract the left-hand side of that expression and the right-hand side, and then do something about it. So in this case, I've got this helper function that says, well, if it's a get call on map, then I'll print a match. So the interesting stuff is, how is that implemented? So this is a little bit complicated. You can have a look at it. But I'll show you a quick demo again. Here we go. I've got a file called test.java. So it's a random file, just for the purpose of demonstration. So it has a method that takes a hash map as an argument, and then calls get Maurice equals null. I've got another one here as a local variable that checks if I call get Ben on it, is that null, and the other one, Martin, not null. So this tool should kind of report those two cases. So you can run that using this command. So first you need to jar up your plugin, and then you can pass that on to the compiler using this command. So processor path would give you the jar file location, and the plugin argument here gives the name of the plugin. So this works like that. Let's run it. Boom, we found two matches, line 6 and line 12 as expected. Here you go. So conclusion. So I feel like hacking the Java compiler is a lot of fun. You're able to kind of enhance Java. So if you don't like Java, well, just make it better, modify the compiler, and you can do some interesting stuff. If you like to use the APIs and do source code analysis, you can do that as well using the libraries. So something I found really useful for this. So in my research, I'm interested in how certain language features are used. So wildcards are very controversial. Generics are very controversial. What kind of idioms do Java programmers use that maybe we can make better or make a language construct out of it? So we need some kind of empirical evidence of those uses. So I'm able to do that by creating a compiler plugin. Thank you for listening. I'll take questions.
In the first example with the Elvis operator, you
Yep.
you mentioned that you have to first evaluate the expression and save it
Yep.
in the local. And did you show that in the source code?
So in the code, I didn't do that. So I was saying this works if the left-hand side is side effect free. So,
It's a bug.
sorry?
So you introduced the bug to the compiler.
So if you wanted to implement Elvis operator like really formally for the Java compiler and use in production, then you would have to check that you put that into a temporary variable. For the purpose of presentation, I want to keep my code simple. So I'm just showing an AST node translation. So it's not a bug. Provided that it's side effect free, it works. If there are any side effects, then do a little bit more implementation.
But in the Java specification, it's not required to be side effect free.
No, it's not. But I'm just hacking away. I'm not interested in making a formal proposition of an enhancement to the Java language.
Did you actually have the full example? Because here you only change the parser. It's very easy then.
Yep.
Did you implement the full version with the temporary variable?
No, I didn't. So another way to do it would be you'd create a new abstract syntax tree node that represent what an Elvis expression is. And then based on that, you'd make sure that the translation is correct. Yep. Yep.
So, for example, there is some Java library for which I want to kind of generate whatever. So maybe Ruby code or Scala code or something. So then I hook into that gen phase or what?
So
Then I hook with a listener into the generation phase. So I'm parsing the source code of a library.
Yep.
And then from then on I can just generate whatever I want.
So I'll rephrase the question, see if it's correct. So given some Java source code file, you'd like to compile that down to a different representation than Java bytecodes. Is that correct? So what you would need to do is create a Java compiler plugin that would be plugged in after the semantic analysis phase. And then you're free to translate that to any representation you want. You just need to write a visitor for it.
And so in the internal data structures you were showing, because I already saw some constant packages, the internal data structures, are they part of the visitor thing like that? Is that
Yep.
part of the standard JVK, or are they very specific to the whole compiler plugin?
Okay, so the code that I show is the public API. So it doesn't use any internal API. So actually, that's some work that I did with Jonathan, which is how can we migrate specific visitor from the Java compiler to using the public APIs. So the code that is on GitHub is completely free from internals of the Java compiler. Thank you. Cool. I think there are no more questions. Cool, thanks again.